Okay, so I guess we can start. My name is Dominik. I have just arrived here from Kraków, where I work in Ocado Technology as a software engineer. But today I would like to tell you something about my private project, which is Flytrips search engine. So today I will draw the idea behind the project for you. I will also present you a website, and then we can dive into some technical details. I will describe the application's architecture and the algorithm behind that. Okay, so as I mentioned, Flytrips is my hobby project. I do it in my free time. We started, I don't know, over 1.5 years ago on the hackathon in Krakow. We had 24 hours to build some kind of application which could support, which could help people to travel. So I came up with this idea. And I was a student at that time. As you know, students doesn't have much money. And I was looking for some cheap flight tickets to visit some places. And the case was when I found something, it turns out that the return ticket was, I don't know, maybe 3 or 5 times more expensive. So I was trying to figure out if this, if it is doing by purpose. That low-cost airlines are trying to get more money from us. So maybe there's some way to not pay so much for the return ticket. So I was manually searching on Ryanair website for flight like this, which are from few places, and that was the idea. I found some really interesting trips manually, but we decided to try write a software which could do this work for us and share this software website with our friends so that they can also use it. We can, of course, go even further and try to find a trip which goes through 3, 4, 5, or 7 places. We call this Euro trip, and yeah, that's the main idea behind this project, to find the cheapest Euro trip which goes through few interesting places and keeping the prices low. Okay, so now it's time for a live demo, and I will show how my website works. So we are in Wrocław, and we'll be looking for trips from Wrocław. I choose Wrocław as a departure airport. We are going to visit 2 places, and we are going to stay at least 1 day in each place. And here we are. We've got interesting trip through Malta and Athens. And it is about 81 euros for all 3 flights. We are staying 2 days at Malta and the next 3 days at Athens. So this list is really, really long. We've got hundreds of proposals here. So let's go further and try to decrease the maximum price. Let's say 70 euros. We can also want to visit like 3 cities and stay minimum 2 days in each. So let's try to find some trips. We need to wait up to 8 seconds. Oh, and here we are. The first one is through Brussels, Barcelona, and Malta. And of course, the price for those 4 flights is 67 euros. Let's go deeper and decrease the price to 50 euros. Maybe we can find something. As you can see, now the searching was pretty fast because this price was really, really low. So the search engine doesn't have to search through the whole graph of flight connections because this limit was too low. As you can see, there are also trips from Wrocław in this price, but the places are, I would say, no, it depends who wants to go where. But this is, as you can see, Brussels and Gdańsk and Stockholm. Okay, so get back to slides. Now I will, yes, please. Yes, of course. I will show you this right now. Okay. Currently, we support only one place. Let's say Barcelona. And currently, it's not. However, in the future, we are thinking about adding some other search options. I'm sure it will allow you to search through the whole countries soon. Yeah, yes, but we try to be completely different than Skyscanner. As you can see, you can only put departure airport here. Yeah, basically that's the whole idea behind it. So let's get back to slides. And now I will run into some technical details. Firstly, what we need to create such search engine or any kind of flight search engine. The most important thing is the data. We need to find some data provider which could serve to us some information about flight prices. Then we need to create application which will build graph connection, flight connections graph, and perform the search. This is the architecture overview of our application. And as you can see, there are 3 main components. All of these components are running into Docker containers. And there are separate applications. So firstly, data provider is a simple REST interface for us. And it allows to download flights for a given airport for a given period of time. We created so-called scheduler application. It is named scheduler because the main component is based on scheduler task from Spring. It runs every 6 hours and downloads the data from the provider to refresh the prices. Yeah, the next component is our persistence layer. This is single node Redis instance. Redis is an in-memory key value store. We chose it because it is very simple to use. We don't need a huge relational database here, and it is very fast. The scheduler application persists all the flight data into Redis data store. And the last component is our front-end application, which exposes REST interface for client, which is web browser. Front-end application also builds flight connections graph and perform the search. We download data about the flight prices from our provider for 3 months ahead. We've got some kind of limit on HTTP requests, and we cannot do more. We support over 90 airports, and this gives us more than 500,000 flights in our data store. And for example, running the current search algorithm for 8 seconds produces 60,000 results. So we cannot present such amount of data to the client. We also need to choose the best one. Okay, so in the search, client specifies, as I mentioned, the departure airport. And we need to return to the same place. The client also can specify how many cities he's going to visit, and he can specify time interval between the flights. It means how many days he wants to spend in each place. Of course, he don't want to visit the same place twice, and we have to display only most interesting trips with the top destinations. So how we build this flight connections graph? Actually, it is pretty simple. Graph is built from nodes and the edges. The edge has got the starting node and the ending node. All the edges are directed. That means you cannot go backward. Edges in our case are the flights, nodes are the airports. On this data structure, we run recursive function. It is similar to DFS algorithm. However, we specify, we limit recursion depth. This limit is a number of cities the user wants to visit. There is also a budget limit. So if you are running out of money, we don't go deeper. And we are trying to find as much cycles as possible in this graph. So here is example of such search. Let's assume that we've got 20 euros to spend, and we're starting in the point A. We can choose the path with the cost of 3 euro. We are going to the point B. And from the point B, there is no flight that is below 17 euro. So we need to return to our point A. We are choosing the other path, the other flight, and we are flying for 5 euros to the point D. From the point D, there's only one flight to point E, which we are choosing. And in the point E, we've got 7 euros left. As you can see, from the point E, there is only one flight that is below our budget limit. And here we are. We found a cycle in our graph. Pretty similar. We also this was the first cycle, but we also can continue the searching and see what we've got from the point C. That was the algorithm. It is, as I said, similar to DFS. However, we are thinking about changing it or going into Neo4j. This is data store dedicated for graph with built-in algorithm to perform such search. Okay, but the main technology stack in our project, the main language we are using is Java 8. We decided to choose the technology that we know very well because we had only 24 hours at the hackathon, so we didn't have time to learn. Those Java and Spring applications are running inside Docker containers. We've got Redis data store, Nginx for HTTPS, and the security headers. And the client uses JavaScript's very simple browser application. Yeah, we've got big plans for the future. Maybe we will have opportunity to cooperate with some other websites which are more popular, like some of you mentioned Skyscanner. We also going to improve our search algorithm and maybe go into Neo4j and promote Flytrips in social media. Currently, there are very few people which are using our website, but I think it will get popular soon, maybe. How you can find us? Just type Flytrips.eu on Facebook search bar. We've got fan page. You can also visit our website. If you want to contact me directly, just write an email. I think that's all from my side. Thank you for your attention. Yes. Yes, we are choosing the lowest price. I think I don't understand you. Yes, it happens it happens all the time, as you can see. Maybe not here, but yeah, because we are looking through Barcelona. But give me just a second. I think I will show you. Okay. So as you can see, these two first trips are pretty similar. First and third. And I don't see the difference, but okay, the difference is in time. Now, is this what you mean? Okay. Yes, of course. You can always stay one day in each place. This is yeah. This is minimal is one. Ah, okay. Sure. I know what you mean. We are thinking about it. But at this very first version, we don't want to overwhelm the user with plenty of options. Possibly we um, yeah, perhaps perhaps something like that. Yes. Thank you. We are doing maybe front end is not a good name for that part of the system. Actually, it's rather backend. But we name it front end because it exposed REST interface for the web browser. However, this is Java application, and it gets the data from the Redis instance, build the graph inside this application, and then perform the search. No, we don't. We are thinking about going into Neo4j. This is a graph database and dedicated for graphs. No, this is simple Java class. Node and the edge. Node is airport, the edge is a flight. Yes. And the dates. We are working with single data provider. Kiwi.com. Kiwi.com. Uh, uh, they provide, but I think it depends on the contract you have. Yeah. Uh, we don't have how many requests we want. It's like 10,000 a day. Yes, that's true. No, yeah, that's true, but the minimum time you want to spend in city here is one day. So we don't care. There's not such problem like transit flights, yeah. If you have any more questions, please just find me somewhere here. Thank you.
Okay. So hello and welcome everybody. As you can see, the title of the presentation is When Grown Men Cry, because when you start doing live coding and multimedia handling on in your Java code, there will be some occasionally you will watch your video, the one video that you watch over and over again, that will be desynchronized. Some of us afterwards have a trauma of watching videos over the internet because they watch even the slightest desynchronization between when somebody's talking and the audio that's being presented. And when you see it over and over again because of different problems, then you begin to be scared you're going to see it again. Some of the friends that used to work with Hulk, our today's hero, or the anti-hero actually, refuse to come to this talk because they suffer trauma all the time and they don't want to go back to it. They move to other projects. So let's meet Hulk. This is the best of the best, the top-notch developer. He can program in any programming language, including Perl. And he of course loves Java, right? So his main focus is on the Java language. And he thinks he's a rock star. When he comes into the building, everybody has to give him high five and treat him specially. And he started programming not to talk to people. He puts his headphones and he likes coding. That's what he does all the time. So he was presented with this opportunity by his client to do a routing software. So on the input side, as you can see, we have a video source that comes from so-called encoder. Then his job was to do RTMP to RTMP translation by using HTTP endpoint to get the configuration and then transmit it over to a bunch of destinations. But the protocol used was an RTMP, which some of us know from the application called Flash, which was at certain time, it was the only way to present multimedia over internet. Then at some point, I don't know if you remember it, Steve Jobs said there will be no Flash on his iPads, and iPads still show you a special icon that there should be a Flash content on a certain part of the web page. So as some of you might think, the same thought Hulk, come on, Flash is dead, RTMP, who uses it? And he was surprised to find out, so he started analyzing it. Okay, so what big players still use RTMP, he thought. Well, let's see. We have our favorite, I think one of the most well-known service for video content generation or publication on the internet. And if you want to do live streaming, you will see this screen, and in the red box you can see the prefix of the protocol. It's RTMP. So the thing that Lena does, some of us and Hulk used to do every day, starting the stream and seeing the gray, instead of this gray icon, the icon goes green. That means that's your stream is online. So let's see another big player for live streaming, Facebook. I don't know if you know, but Facebook also offers ability to do live streaming. And again, the red box, oh, sorry, I was supposed to play laser. The red box here says RTMP-S, which is actually encrypted RTMP over SSL. So we know that there is a bunch of destinations provided by big players in the market that allow you to stream into RTMP. But let's see if there's a software for it. So there are so-called encoders, and probably you know the first one, right? Anyone here who never heard of FFmpeg? Nobody. See, everybody heard of FFmpeg. It's a Swiss Army knife of video and internet encoding. You can use it with a variety of formats. It supports almost everything. Whenever something comes out, there's a community behind it that adds a plugin, or there's somebody who tells you how to use it. So you can use it with almost everything. There's also a commercial tool that offers the shareware version called Wirecast. And during this presentation, you'll get to know some of the intricacies of Wirecast and how it behaves in certain situations. So you might have heard also of the open source software called OBS. This is also a software that allows you to stream directly from your computer as a live stream to an RTMP destination. The company you might not have heard of is a Teradek, so it offers a hardware encoders. This means that you record a video and then it's automatically encoded into H.264 and then transformed into RTMP. And the last one in the list, so when the project started, Elemental, was still a separate company, then bought by AWS for some, I don't know, millions of dollars. I don't know, Americans only show their prices, you know, the American businessmen only in millions of dollars. So I lost track of it. But when the project started, the client says that will be Hulk's biggest competitor. He wants to build software exactly the same as Elemental, and now part of AWS. So you see, it all fits, right? There's a bunch of encoders. You can really choose how you want to stream into your destination. Then there's a whole variety of destinations. And the software in the middle was supposed to be doing so-called routing. So getting one stream and then split it into different destinations, still maintaining its quality and do it in a very high performance manner. So you might think that the first thing that did not work was audio video synchronization, but no. This is something that probably most of us know, right? Anyone tried to use Skype and seen something like this? This is something that happens when your stream starts incorrectly. But this was the first thing, the first challenge that Hulk was given, and this was due to how encoded stream is has structure. So it starts with a keyframe. You might consider a keyframe as a bitmap. So it contains the full picture, and then you have a bunch of so-called B or P frames. I don't know who invented the letters, but that's an industry standard. B, those and the arrow pointing there show you in which directions those frame can look for the pixels to build the full picture. So B frames can look in both directions, back and front, and P frames, I think, only in backwards. So if you start somewhere in the middle, the frames that are actually the partial frames will not have the reference pixels, and that's why you'll see the green pixels. So if you start the stream, if you start the stream like this, there is an encoder that connects to your router, right? Then it says, okay, the connection has been established, and you can start coding. Then you have a REST endpoint that provides you with a configuration, and then you can also start the streaming at the same time. And then after some time, you will get to contact your destinations. All the things happen in parallel. This means that your stream might start in a very not optimal place, and then you'll see those green pixels. So, and then let's assume this is our simple router. The stream starts with decoder configuration for audio and video. That's why there is a metadata. Then you build a buffer. So when your destination is ready to receive your stream, you guarantee that it's received starting from a keyframe, so nobody sees those green pixels. And then you have two things that are that happen here. You have a frame handler and output connection. So the buffer you see here is shared among both frame handler and output connection. Frame handler is on the input and output connection is on the output side. And then, so whenever you receive a frame and it's a keyframe, you clear your buffer and append a frame to your buffer, right? Because you need only one keyframe to properly start your stream. And then when you get so-called interframe, so anything that's in between, you simply add it to the buffer. And of course, in order, because it's a shared state, you need to protect it against parallel access. So when finally your connection is established, you get your callback notified because it's all in asynchronous. And then you first start writing your metadata and then your buffer. But you see, there is one thing that happens here. If you do high performance computing, there's one thing that might be improved here, right? Do you see what it is? Because of the shared state, the thing here needs to be synchronized, right? So do you know a way to avoid this kind of synchronization and still maintain this flexibility of providing the buffer into destination? So if you look at this, do you see any potential thing that might be changed here to avoid these explicit synchronization mechanisms. Why two buffers? Yeah, I know, but we need this shared state because then the input connection provides us with the stream we want to deliver to destination. So we need to have one. What? Volatile, that's one of the options, exactly. But if you still want to have some solution in the collections framework, you can also introduce, anyone would like to guess? That's the direction, not mutable, but there is a copy on write array list. That was the direction, right? So you don't need to do explicit synchronization, and this way, see, this code became very, very cleaner, right? We don't do synchronized blocks in the handling of the frames. We don't need also the explicit synchronization on the destination side. This was the first Hulk's challenge. Because of this, his code would be improved because once you access the iterator on copy on write array list, you get immutable state of your array list, and then any other changes are not affecting your view of the list. But still, think about it. What happened here? If you were supposed to be thinking what is still wrong with this code, because we have a copy on write array list, and do those is this shared state somehow mentioned to all those users like frame handler and output connection? Not really, right? We got rid of the synchronization blocks, but we're still using the list. So if anyone else would update the list into non-synchronized or something or other structure, we would get lost. So that was the first thing Hulk had to think about it. And you know what he did? He thought, okay, now I'm going to answer more trick questions on my interviews. So those interviewers are going to love me. And then this went pretty fine, but this also forced him to look through all the code that was developed by other developers. So you know how this is called, right? It's called a technological debt that grew bigger and bigger. So then his first challenge with audio-video synchronization happened when they switched from FFmpeg into Wirecast. I told you that there's going to be a lot about this specific software encoder. So, and there were two scenarios here. When the connection was established really, really fast, like on your local machine, everything was fine. But when the connection was established slow, they saw this audio-video synchronization for the first time, unfortunately. And see, this is what happens when you receive a stream from this encoder. It gives you a small delay of the audio stream. So then, after analyzing, they found out that there's a small delay on this stream, and that's why it's then propagated into the output. Normally, if you have this kind of offset, you do something that I do. You can see it's a clapper, right? So we have both visual representation of when your stream should start, and if you see the red box at the bottom, there is an amplitude change. So that's why they use it in the movies. They record audio and video separately, and then they have a visual way to set it up. But if you do it in a software, it's a bit more complex, unfortunately. So you see the stream starts with an initial offset, right? And then you have another keyframe. The keyframe guarantees that from this point on, the video and audio is synchronized, right? And you have two scenarios. One that everything works fine for the fast connections, and that there is desynchronization when your connection is established, your destination responds slower. So what do you think, which one was more common when they started testing it? When the fast connections or the slow connections? So remember, there is an encoder, there's a cloud, and there's a destination living in different destinations. So outside AWS infrastructure. So which one would you think happened more often? Yeah, well, the testing was in a more like production environment. So they were streaming from their location into the cloud and then passing over to YouTube. So you think that it was established fast or slow? Yeah, that was the thing. So it happened slower. And do you know why it happened? Because the buffer did not contain this offset when the connection was established slow. So the offset was captured first when there was a connection established, and then when another buffer was gathered, the offset should be dropped. And it was because it was really, really slow, so he had to do one thing: pray. So you see here that this first video frame of the metadata has a zeroed timestamp, right? So statistically, the scenario when the connection was established really fast should not happen. So he changed it into 0 and simply prayed, and his client accepted, said, it works great. So that was the first solution he did for the audio-video synchronization. And then his client came back, okay, said, now that you know RTMP, I want you to strip into two separate streams, into raw H.264 and raw AAC, and then build an MP4 out of it if the client requests a specific time period of this initial stream. Well, he knew RTMP already, and then he only needed to learn how H.264 and AAC are built. So you see, those keyframes were delivered in 2 seconds intervals. So this is the amount of data, or actually the files you're getting when you're doing a live stream over 60 seconds, over 1 hour, 1 day, and then 1 week. So this software should write continuously files. And guess at which point, oh, I'm not sure if this is so visible. So we get 60, 3060, 86,000, and then something over 400,000 in case of a 1 week stream. So what's your guess? When it stopped working? After how many files was written? 60, 3060, 86,000, or 400,000? Exactly. Even not full 1 day. It was 60,000 files. But the test lasted 1 week. And then if you start streaming at 30 FPS, you get this weird frame duration, 33.3 in a period. I mean, of course, mathematical period, right? And then since RTMP does not support floating points, you get either 33 or 34 because it's rounded, and then the reminder is added to some upcoming frames. But for the AAC, it's pretty simple because you get 24. And RTMP also passes then 24 as the duration of the frame. But occasionally, Wirecast started sending different times, different duration. It sent 66 or 100 milliseconds for a single frame. And that's when, for another time, the video got out of sync because it was saved into a binary file. But how was it possible that video was sent without consecutive frames, and that encoder mentioned that it was lasting longer? So the answer is dropped frames. I don't know if you ever try to do watching a video or trying to export a video on a software that had very limitations on the CPU usage. So you might see this kind of a warning that because encoder was not capable of producing your stream, it will start dropping frames because video encoding is a very resource-consuming process. So it might tell you, I'm not able to do it, I will start dropping frames. This is actually from a software called Final Cut Pro. Wirecast has also an indication of the dropped frames. And you first see it, you might even overlook it because it's not that clear. But then, so where exactly is this time present? Because the idea was to save raw H.264 and AAC. So you might be wondering which part of this live streaming stack contains time information. This is a small example Very simple, right? It's a very simple example of what you're dealing with here. So we start with containers, MP4, RTMP, HLS, QuickTime, MPEG-. And only one of their content might be H.264. So you get, first you decide encoding decoder capabilities. Then you do, what's your next, you say, what's your next network abstraction layer? This is where those metadata and BP iframes come. Then you say, will I be telling my decoder what's the FPS? And then you have all those layers like slice layer and macro blocks and then motion vectors and how the pixels travel through the screen. So it's all very simple, right? Just to start with one format of the video. And you know, some of them also have even more complicated extensions. But going back to the time, where is the time stored? Do you, when would you, if you were supposed to be guessing, which of the formats contain information about time and duration explicitly, and which one just contain the binary representation of the stream? Guess, which ones? Yeah, it does. That's one. Well, actually, all the ones at the upper part contain time information at some form, either by providing you with an FPS or by the so-called frame reorganization. But the lower one does not. So the same goes for AAC. It will not tell you in the binary form what's the duration of your frame. So unfortunately, if you receive your stream in a binary form from H.264 format, you might be a little lost. And then, so you have these holes in your video, and when you start saving it binary and then building an MP4 out of it without explicit time information, you get, again, out of synchronized video. So then Hulk needed a solution for this, and he needed to find a way of contain this information in a format that's not really that does not really allow it. So then so when he thought about it, he thought, you know, the number of layers, so that he need to go deeper and then search for a solution. Luckily, H.264 format was developed at the times when they're when the disks were really slow, and disk cache for providing the coder had to be maintained in a very stable way. So that's why they introduced the filler data item. Filler data does nothing. It's so-called non-video coding layer. It's completely ignored by the decoder. And it can contain a payload of your choice. So actually what Hulk chose was to include the filler data as an indication of an empty frame. There is another option in H.264. You can build a frame that tells repeat the previous one, but then you need to build actually the whole structure of a video frame, which is much, much harder than just adding an empty message. Yes. Well, I would prefer. Very good. That's one of the solutions that he started with. But eventually it looked like the video was cut. So it wasn't a viable solution because the frames lasted slower, and then the video also was cut in random places. So for example, my speech would be cut now into small pieces, and you would hear it as a chunk of something that went not good over line. And this was really, after testing, he found out that it's not a good solution. But thank you, it was a good question. But eventually, he ended up with his custom H.264 that only his software could understand in order to support the dropped frames. And then he was supposed to build an MP4 out of it, but you know, since the binary format already contained information about drop frames, there was another solution. There could be an extra file that would say, okay, this and this frame lasts longer, right? But then you would need 3 files and not 2 files to express your stream. And this way, only by reading a binary stream and parsing H264 that was done already in his application, he was able to provide an extra time information for the MP4. MP4 was supposed to be built, even for those very long files, 400,000 files, with less than 2 seconds. And I told you that it stopped working after 1 day because, oh, we'll get back to it later. So the MP4 format. The MP4 format is usually pretty simple. You get a tree, which is a tree of so-called boxes. And then you contain the metadata, decoder configuration, you get everything you need. But there was a slight problem. You see the last box here, the MDAT, is just 1. It contains your full audio and video data, and it needs to be built ahead in order to provide its size. So the requirement for responding in 2 seconds for a very long streams, if you need to compute everything, would not be fulfilled. But there is an extension to MP4 called fragmented MP4, FMP4. And as you can see, it's much more suited for this kind of approach, because you first build a MOV, which is a metadata, which is built really, really fast. Then you get a movie fragment, which is actually the 2 seconds part of the video. And then you only need to provide the random access file box at the end. So this was perfect. It all started working. But still, how could this one question regarding the video format? There is so-called timescale and num-unique syntic, which was pretty awkward. I'm sorry, unfortunately, my formula here is a bit hidden, but I hope you can see. It was a bit awkward because for 30 FPS, it's for computing how fast your video is going to be played. And then if you have 30 FPS, why do you need this division? You get 30,000 by 10 by 1,000, you get 30 by 1. So what do you think? What's the purpose of this a bit more explicit way of denoting the frame rate? Can you guess? I guess not. But the solution he found out was the answer. You can find the answer here on this slide. So you have timescale and num-unit syntic give you the frame rate. And frame rates can have decimal points. So you get 2997, and you never compute, when you compute the frame duration, you then divide it by the found number. So you stopped getting 33.3, but now you're getting 33.3666 something 7. And this is actually the easier solution because it was sent, I told you the hardware encoder Teradek sent an extended a bit longer duration of the video frames. But there is also another option called drop frame coding. So for 2997, actually the NTSC format, you can use, you can send it as 30 FPS and then drop frames every minute, except for the 10th minute. And then, as you can see from the formula here, you get proper frame rate. So this is how it's, there are 2 options. You can either send longer duration or start dropping frames, right? And this was the thing, this was the time when Hulk cried because all his assumptions were lost. He had to do a floating point computation and then extend his logic with the way he synchronized his audio and video. And the answer to this was this, even Wirecast used a slightly different divisor. So you don't get 2997, but you get 2997 6023 something. So even at these decimal places, you can get variations depending on the software that does the streaming. You see that, you know, Hulk built a very strong relationship with the Wirecast software. You can see it, right? So, and yeah, so he had to, adjust all the logic and build almost all solution for audio-video synchronization, again using the 2997 encoding. And then there was a list of his challenges. Probably you know the adaptive streaming. If you go to YouTube, you start streaming, you get a very bad quality, and then the quality improves over time, right? So your video is served to you as a 2-second intervals, and if your decoder or player capabilities allow it, and your internet connection allows it, you're going to get a better stream. So this was Hulk's third challenge. So to do adaptive streaming, you need to do a stream in the 4 or 5 different resolutions and bit rates and something. But for this, he needed a native piece that was doing the actual transcoding, communicating with his components asynchronously. So he was sending that H.264 and receiving H.264 prim. You might see that I'm reading recently some of those research papers, so it's a prim. Can you guess why it's a prim and not H.264? After transcoding, well, some of the dimensions are resized, right? But for the same dimension as input, you get the output. Why is it a prim, not the H.264 exactly? Because it's just an equivalent, a visual equivalent of your stream. This means that the viewers will be able to see exactly the same, like recording from here, but internally the structure of the H.264 will be different. So the first solution for merging, and then you see that it's received in the merge layer and then synchronized with audio. So the first idea was to number the frames of the incoming stream and then match them on the output of the transcoder. But unfortunately, you could get 3 frames on the output, this H.264 prim, as 1 for the input. This unfortunately couldn't work. So another solution was to get this simple way of handling it. So when you get a transcoded frame, you start compare it if your arrival time was fine, and then you see if your if it was later than your arrival time. This means that the audio is already there, and we can flush the buffer. And then, if it doesn't happen, you just append it. So you wait for the audio that it's supposed to be coming, and you sort it. So, do you think that this is a good way of handling it? Do you see any potential issues with this solution? So from the audio-video synchronization perspective, it worked fine. But unfortunately, after some time in the production, they found out that their servers, the 16-core servers, were using 100% of the CPU. And they couldn't find out why. So they started investigating. And so just to give you a hint, the writing of those 5 streams for the adaptive bit streaming takes about 2 seconds. And then it's written to a EFS, which is actually an AWS version of NFS, which is pretty slow. And then this EFS can have hiccups. It can prevent you from writing your stream for some time. Normally, the client will not see it because the stream on the client side is cached, right? So the playback is maintained. But what do you think happens if the write time is around the same time that the video arrives, and then for some time it stops? So what happens with these buffers? Will they be cleared? Not really, yes. They start growing. So after a while, they found out that adding more and more items to this list began to grow so much that the sort operations took all the processors. And unfortunately, the servers went down. So at that time, do you know what this picture is? A black hole. Exactly, that's a black hole. So they figured out a way of describing it, that if your server goes above 70% of the CPU usage for 1 minute, it crossed the event horizon. It's on the way to using 100% of the CPU, and it's a thing that needs to be replaced. So after a while, and the problem is that you usually get very little symptoms, so you need to guess, right, what to do with it. So they chose to introduce a tree map. You know what a tree map internally is and what algorithms it uses? Exactly. It uses a binary search internally. So it's if you have a key right here, this arrival time, you can use it as a way of structuring your data, right? And then those searches are pretty fast. And that way, by just replacing the collection that allows sorting and ordering of the items, the problem was solved. So it disappeared. Luckily, this tree map has a interface called sorted map that allows you to do also queries based on your keys. So it solved all bunch of problems for Hulk. And they went into testing for 5 days. So what do you think the last thing? You have everything fixed, right? You trained it for 1 day, you tested it for 1 day, and then you saw that everything works fine. You go into production and you start 5-day testing. What could go wrong here? That's true. But, this slow running tests, I mean the short ones, up to 1 day, prove that everything works correctly. The buffer was cleared, everything went fine, the video was delivered, the connections were established. In case of any errors, they were handled. But there was one thing that was still left for the long-running test. I remind you that we have a decimal point here, right? So we have 33.3 infinitely, and then we have frame durations that are 33.36667. Right? And for audio, it's still 24. So does that gives you a hint what could go wrong here with all those decimal points? Assume you want to add just a double in Java for one or, I don't know, over 1 week. And one of the values is an integer and the other value is double. So what can happen to this double? Exactly. It might lose precision. That was the last challenge of Hulk, and the last time when he thought he was safe, he started his streaming for 5 days, and it was out of sync again. But you know what the solution is? It's also pretty simple. You just need to use consistently a format that supports higher precision. This is in Java supported by big decimal. You can provide a math context that tells you how many decimal points there are and what's your rounding strategy. And then all the operations are expressed as big decimal operations that do replace the arithmetic operators known for primitives. And that was it. That was what solved it. Unfortunately, you get a bit of an overhead for the big decimal, as it's not you can't use plus or minus anymore. But that was it. Replacing it consistently with a big decimal solved the problem, the last problem, the long-running one of audio-video synchronization. So I hope we have some time for questions. Do you guys have any questions? Yeah. Yes, potentially, but tree map internally uses binary search, which is more efficient for finding elements. Well, hash contract has some advantages. It's not as explicit as tree map, but maybe it wasn't tested. It wasn't verified that hash map might be a good replacement here. Well, actually, in this project, there was no direct connection. So the MP4 was built afterwards based on the stream data. So you're saying like you want to connect destinations in the same time. Oh, okay. So that's the adaptive streaming. You can save HLS, and then the browser supports this format and can play it on live. You don't need direct connections between both parties. There are newer protocols like those WebRTCs that are peer-to-peer communication, but it wasn't used for those live streaming scenarios. Anyone else would like to ask questions? Well, usually, if you're just receiving the stream, you don't need to do any heavy computation because the stream is received at the same time when it's recorded. Like we're recording here, so you cannot serve your stream faster than it's happening. Well, you can use FFmpeg for this, but that's not really usually a real-world scenario for live streams. So it's not really that memory consumption is not really a big issue here, unless you get, some of the buffering or handling of your data wrong. Because those buffers are really small. For 2 seconds, you get something like hundreds of thousands just of frames, so it's really small. So maybe you did the transcoding part, where you had to re-encode the video. Okay, so in that case, you don't need really a lot of memory. Anyone else would like to ask a question? Yes. Yes, it has to be ordered. By the arrival time, so the time when the frames arrived in the system. They had to be sent after getting the transcoded data in the same order they arrived. So hash map is not a good choice, right? Okay. Anyone would like this question? Maybe in that case you need, instead of 12, you need like 100 decimal places, right? But luckily for this project, it was never verified. But this is part of the empirical data. So after 1 week of testing, it was proved. Then somebody did again 1 week and 2 weeks of streaming that proved that this decimal precision with 12 points was enough. So maybe you're right. Maybe after 1 year, it would still be, still be not enough. Okay, so in case you're doing live streaming, save my email or my Twitter and contact me. I'll listen to you. I'll give you my ideas. I will even play you on my flute as I'm playing flute at home. I will tell you that my kids are more troublesome than your video stream. Just, contact me. And if that doesn't work, I'll come and hug you. Thanks very much for your